All right, today we're going to talk about the end behavior of polynomials. And to do so, we're going to first define some terms. So the degree of a function is the largest exponent when a function is written in standard form. Okay, so then remember, standard form is when you have your exponents all Remember, standard form is when you multiply out any of your parentheses that you may have, or anything like that, and then you also combine your like terms. So you can't simplify it any further. That's standard form. So if we had y equals 2x to the third minus 6x to the seventh plus 2, your degree would be the highest exponent you see. Don't fall for the trap and always look at the first term, 2x to the third. Look around to see what is your highest exponent. Our highest exponent here is 7, so our degree of this function is 7. Now the next one is the leading coefficient. The leading coefficient is the coefficient of the variable let's write that a little bit neater. With the highest degree. So if we look at this function here, y equals 4x to the fifth minus 3x squared plus 11, my leading coefficient, or LC for short, would be 4. Not because it's the first coefficient, but because it's a coefficient of x to the fifth power, and that's my highest exponent, my highest degree. This is a fifth degree function because my highest exponent is 5 and my leading coefficient is 4. If we look at the one over here in red, your leading coefficient would be -6 because that's the number in front of our highest degree term. Our highest degree there was 7, and the number in front of that is -6. Now, a polynomial is just a function of with terms. A function with terms. And we've been working with polynomials all year. 3x squared is a type of polynomial. -14x to the 8th minus 7x to the 6th plus 5x to the 4th is another polynomial. So we just have a bunch of terms put together that gives us a polynomial. All right, so now we're going to look and see, can we figure out the end behavior based on the degree and the leading coefficient. So this summarizes the activity that you're doing. So if we have an odd degree and a positive leading coefficient, so the way I like to think about it is if you have an odd degree function, the ends go in opposite directions. Either the left side goes up and the right side goes down, or the right side goes up and the left side goes down. So a positive leading coefficient means the right side's going up. So remember, when we have n behavior, we have x approaches negative infinity, that's the left side, and we have as x approaches positive infinity, that's the right side. So we're going to have this for every single box here. So I'm just going to write that in each of these boxes, because we will always have a left end behavior and a right end behavior. And the way we say left side and right side is using this notation here. As x approaches negative infinity, that's how you talk about the left side. And as x approaches positive infinity, that's how you talk about the right side. Now, to say whether something goes up or down, you would say y approaches positive or negative infinity. So y approaches, we're going to have that for both of these. So again, when we talk about an odd degree function, the ends are going to go in opposite directions. And if you have a positive leading coefficient, the right side always goes up. No matter what the degree is, a positive leading coefficient means the right side goes up. Well, if the ends go in opposite directions in an odd degree function and the right side must go up, that means the right side must go down. And the right side goes up. And with an even degree function, think about our quadratics, our parabolas. Both ends either went up or both ends went down. And quadratics had an x squared term. That was your degree too. So even degree functions will always have the same end behavior. Either both sides are going up or both sides are going down. And I just said if you have a positive leading coefficient, that means the right side goes up. Well, if it's a even degree, both ends are doing the same thing. So both ends are going to go up. It might be a good idea to draw a rough sketch of what that would look like. So if we have an even degree function like a parabola, both ends are going up if your leading coefficient's positive. An odd degree function, that could look something like this, where the right side's going up and the left side's going down. Now, if we have a negative leading coefficient and an odd degree, it's going to be the reverse of up here with a positive leading coefficient. You could also think about a negative leading coefficient means your right side is going to go down regardless. Sorry, your right side is going to go up regardless. So then that means the left side must go down. I'm going to make that negative sign a little bit bigger. I know it could be a little hard to see. So an example of that could be a line. A line has x to the first power, which is an odd degree. So all lines are odd degree functions. And then the end behavior here for a negative leading coefficient and an even degree, the ends should go in the same direction, so they're both going down. So we could have something that looks like that. That would be an even degree function with a negative leading coefficient. So for this unit, this chart right here is going to be your go-to. This is something that you need to have written down and readily available to you. So make sure that this is in your notes and that you keep track of it. Now on to the next page, we're going to convert these into standard form. So standard form, we want to have the biggest exponent first. That just makes identifying things a little bit easier. So for this one, letter A, we just have to move things around. We're going to put the negative 4x to the 5th up front, plus 3x, plus 10. Then you're done. We're going in order from biggest exponent 5 all the way down to the smallest exponent of no variables with this 10 at the very end. Now, letter B, x plus 1 squared is not x squared plus 1 squared. Think about 7 squared. 7 squared is 7 times 7. So when you are squaring something or raising it to the second power, you're multiplying that thing by itself. So negative 2 times x plus 1 squared is really this. Negative 2 times x plus 1 times x plus 1. So then we need to multiply this part here, x plus 1 times x plus 1, and then we'll worry about that negative 2. So we're going to multiply it using our box method. So x times x is x squared. X times 1 is 1x. X times 1 again is 1x. And 1 times 1 is 1. So then I get negative 2 times x squared. And then I have 1x plus 1x, that's 2x plus 1. And then I distribute this. So negative 2x squared minus 4x minus 2. This is our standard form. So I'm going to pause for a minute and have you guys try these two and see what you get. So go ahead, pause the video, try these, and then once you are done, unpause it to see if we get the same answer. All right, so look at the answers here, and you see what I got for letters C and D. It may be kind of annoying that we just got done factoring, and now it seems to be like we're going in the opposite direction of factoring. But being good at factoring is also going to mean that you're good at doing this because you're doing the same process but in reverse. All right, now let's look at number 2. We're going to have two functions here, and we're going to put them in standard form first if we can, and then provide the All right, down here at number 2, we're going to look at these functions and we're going to identify the degree, leading coefficient, and the end behavior. Now for letter A, we could do what we did up here and multiply it out, but notice we have a squared right here, a second power, and an invisible 1 power here. And this can get very tedious to multiply it out, so we're going to try to find a shortcut. So we're not going to multiply this out. Just take my word for it that this is x to the third minus 12x squared plus 21x plus 98. So now that this is in standard form, it's very easy to see, oh, our leading coefficient is an invisible 1, and our degree is 3. All right, now we can figure out our end behavior from this chart up here, where our degree is 3, which is odd, and our leading coefficient is positive. So this will be our end behavior. So let's write that down. As x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity as well. Okay, so that one wasn't too bad. When we look at something like letter B, we have 3 sets of parentheses, and we have a set of parentheses raised to the second power, 1 to the 4th power, and 1 to the 3rd power. So again, we could write all of this out and determine what the what the function is in standard form. But if we look back up here, look at what I circled in purple, 2 and then invisible 1. 2 plus 1 is 3. Okay. So if we can do the same thing down here where 2 plus 4 plus 3, this will give us our degree. So we get 9. So our degree is 9. This only works if you are given a function in intercept form. These are our 3 intercepts here. We can just take these exponents and add them up, and that will give us the degree. We couldn't do that, for something like number 1a up here. That one's already in standard form. We're not going to take and add these exponents 5 and 1. This only works in standard form. That is the biggest mistake I see when it comes to this problem. Now the leading coefficient, we just look for the number in front. There's an invisible 1 in front. So then we have a positive leading coefficient and an odd degree. So it's going to be the exact same end behavior as the previous one. So you're really not doing much math. You're really going to have to look and understand what that table tells us and how to use it. So I hope that this was a good introduction. I hope that this made a little bit of sense. Make sure you smash that like button and subscribe.